So we've been talking about Z effective. So if you'll remember, Z effective gets greater as we move across the periodic table towards fluorine. And Z effective, again, that effect of having a positive nucleus having an effect on its valence electrons, is also stronger at the top of the periodic table than it is at the bottom. So this gives us this odd effect that fluorine has the greatest pull of its nucleus on its valence electrons, and francium down at the bottom has the weakest pull. And now we're going to look at some of the effects that can have. So one of those is atomic radius. So as in fluorine, as Z effective pulls on its valence electrons and on all of its electrons, since it has a greater pull, it pulls its electrons closer and makes the atom smaller. This is one of those cases where a greater effect gives you a smaller atom. And it sounds strange to say it like that, but a greater Z effective has a greater pull, and the greater pull pulls the electrons closer and makes the atom smaller. The opposite is true then as we go down the periodic table, those energy levels give us those larger sizes. So those are also going to have a larger effect. So this is true both as we go down, we get higher values of N, and that's going to increase the size. As we move from left to right across a periodic table, that's where we're adding protons. And as we add protons, those are going to have a larger positive charge in the nucleus as we go across, having that pull on those valence electrons, and those atoms will get smaller as we go across. For ionization energy, so we need to make sure we talk about what is an ion, and that basically is an atom with a charge, so they're no longer neutral. So these are not neutral atoms. So ionization energy is the energy required to remove an electron from an atom in the gas phase. So when we talk about ionization energy, this is the energy required to remove an electron from an atom in the gas phase. This gas phase is very important because later when we get to ideas about how things react with water or how things react when they're in a liquid or when they're in a solid, those are all different. So it's important for a definition that we're talking about a gas phase. And again, we care about the effective nuclear charge, or Z effective. So again, remember, electrons are precious. So who's going to try to hold on to their electrons harder? Who's going to not care so much? So this is one of those beautiful graphs. What's happening? As we go across the periodic table, so if you look down, we go from lithium up to neon, going across the periodic table. As we go across, the energy is greater. Higher ionization energy means you're putting more energy in to remove the electron. So the greater the ionization energy, the harder it is to remove the electron. And this should make sense because we've got fluorine and neon trying very hard to hold on to their electrons. We have things like lithium and sodium and potassium that would actually probably be happier if they got rid of one of their electrons. So those are going to be down at the bottom. So ionization energy increases as we go across due to that effect. And as you might have noticed, especially watching where the noble gases are, ionization energy is going to decrease as we go down. That is, as we go down and we add shells, it's easier to remove an electron. If it's easier to remove an electron, it requires less energy, less ionization energy. This is where we're now back to about stability. If you noticed, there were some little hiccups in the previous slide, okay? There were these little places where we had a little thing where it goes up and then back down, and up and back down. And as you'll notice where those are actually fluorine between oxygen and nitrogen, and then between phosphorus and sulfur. What's happening is it's harder to remove an electron from a half-full subshell or from a full shell. than it is to remove one from that last one. So when we're looking at a half full shell, it's actually harder to remove it from nitrogen than it is from oxygen. It's harder to remove it from beryllium than it is from boron, because from boron to beryllium, you go back to a full S shell. And that full S shell is a little bit more stable than having one lone electron in the P. Likewise, it's more stable to have that half full subshell like nitrogen does. So it's harder to get rid of the one out of nitrogen, but it's a little more stable to get rid of that one when you lose it from oxygen. So it's another one of those times when that half full is more stable, the full is more stable. So it's much harder to remove it from that group 5A, much easier to remove it from 6A. And it's not much easier, it's noticeably easier. It shows up on the graph, but it's not as big of a gap as it is obviously from a noble gas to an alkali metal, but it's noticeable. When we have ionization energy, we can also have a second ionization energy to remove the next electron. So notice this is removing a second electron. This is not removing two from a neutral atom. This is removing the next one. And then the third is moving yet the next one down. So a grand total of 3, but you remove one at a time. The other thing to remember is these are all positive. These are called cations. That's easy to remember because cat ions are positive because cats have paws. Yeah. It's a pun. Deal with it. Makes it easier to remember. Cations are positive. So it is also harder to remove from a noble gas configuration. So if you noticed, I'm going to flip back again. Back here, neon, super high ionization energy. Way down here in the sodium, okay? Much harder to remove from neon than from sodium. Protons are about the same, but this has to do with the fact that neon's very stable. All of those noble gases are very, very stable. So whenever you're going to remove one from a noble gas, it takes a lot more energy than anything else. So this is really obvious across the periodic table. So when you look at sodium, for example, that first one popping off takes about 500 kilojoules. To remove the next one, which would take you then away from the noble gas configuration, takes almost 10 times as much. Lithium has that same issue, about 500 kilojoules, and then the next one is about, again, 10 times as much. Because once you take one away from lithium, you're to a helium noble gas configuration. So when you take away one from sodium, then its number of electrons matches that of neon. And in doing so, that gives you that nice full P subshell. So again, we're back to where that full shell, the full P subshell, or that full N equals 2 shell is much more stable. So that's what they're trying to hang on to.